Hello and welcome to this IPDPS 2022 presentation on Colza, an elastic in situ visualization framework. My name is Mathieu Dorier. I am a researcher for Argonne National Laboratory, and this work was done in collaboration with Jay Wang from Rutgers, Utker Shayashit from Kitware, Shane Snyder and Rob Ross from Argonne National Lab, and Manish Parashar from the University of Utah. So I would like to start this presentation with some pictures. What you can see here is a volume rendering of data from the Deepwater Impact simulation, which simulates an asteroid crashing into the ocean and making big waves. It is based on an unstructured mesh, and as you can see, this mesh gets increasingly complex as the simulation progresses. We can see that when we look at the number of cells in this mesh as time progresses, or equivalently, if we look at the file size, which grows from a couple hundred megabytes at the beginning to about 15 gigabytes at the end. This means that as time progresses, we have more and more data to store, and it becomes more and more difficult to render. Solving the storage problem is rather simple. The solution is called in situ visualization, and it consists of connecting a parallel visualization software directly to the simulation and performing visualization while the simulation is running without storing anything. Solving the increase in rendering complexity, however, is a lot more challenging. If we allocate a lot of compute resources up front, we will waste them at the beginning when when things are small and easy to render. But if we don't, we won't be able to render the later iterations that are a lot more complex. So we need to be able to add in situ compute resources incrementally as the simulation progresses. And this is unfortunately something that none of the existing in situ visualization frameworks can do. Here you can see another example. This is the nucleation process in the LAMP simulation, where the number of particles to render increases over time. And this is another simulation that could benefit from more flexibility in the amount of compute resources available to perform in situ work. And overall, elastic in situ is a key to enable faster scientific discovery. Beyond simply allowing users to add and remove resources while their simulation continues running, it enables them to change the type or the frequency of in situ visualization that's being done. It enables smarter workflows that can adapt to, for instance, the content of the data or the performance of the simulation. And it can even be used in conjunction with malleable jobs, allowing job schedulers to make a better use of the resources at the scale of the entire machine, which in turn enables better resource utilization. Unfortunately, current in situ frameworks are not built for elasticity. From an algorithmic perspective, parallel visualization algorithms assume a fixed number of processes. But since they have been optimized for decades, we cannot just throw them away and start over from scratch. This would take years and for little benefits. We could shut down a job and restart it with a different number of processes, but that would mean checkpointing its state, storing data, which is something that in situ visualization specifically aims to avoid. The second reason why current in situ frameworks are not built for elasticity is that they all rely on MPI. And MPI has very little support for dynamic process management. Sure, we have things like MPI ComSpawn, but that's either not supported on some platforms or very complicated to use, especially in the context of in situ visualization. Even worse, some frameworks like Damaris, for instance, are tightly coupled to the simulation via MPI, which means that it uses it for communications between the simulation part and the visualization part, even splitting MPI world to share resources with the simulation. Which means that in this context, any attempt to rescale the visualization requires changing the MPI runtime, and it requires changing the simulation as well. So a potential solution to this problem, which is the one that we will explore in this talk, is to replace MPI in existing frameworks with a communication layer that enables elasticity. If we look at how tightly coupled to MPI the existing frameworks are, we can find that some have already abstracted their communications. For instance, VTK and ParaView have the concept of VTK communicator and VTK multiprocess controller, which are abstract classes with concrete implementations using MPI. We find the same in ICE, the image compositing library that is used internally by VTK. And in frameworks like Damaris, which has a concept of reactor and channel that are also abstract classes with implementations based on MPI. And with a bit of work, we find that some other frameworks like DIY and Visit could enable some abstractions in their communications that would allow MPI to be replaced with something else. So realizing that, we decided to implement an in-situ visualization framework that does not rely on MPI for collective communications, but that can still use existing in-situ frameworks like VTK, like ParaView, for the actual analysis and rendering tasks. Our framework is named Colza, and it follows the typical architecture of a staging area, which sometimes is called in-transit visualization. This staging area spawns a set of nodes that receive some data from the simulation through the network, and that executes analysis and visualization tasks on the received data. We do not aim to make the simulation itself elastic. This is another problem. What we aim to do here is to be able to add and remove nodes from the visualization part, so from the Colza staging area, without shutting it down while the simulation is running. So Colza is based on the Mochi suite of libraries for HPC microservices. Mochi is developed by Argonne, Los Alamos, Carnegie Mellon University, and the HGF group, and it has received recently an R&D 100 award. Internally, each process of the staging area runs what we call a Colza provider, which is an object responsible for listening for incoming RPC from the simulation. And these RPCs are then dispatched to user-provided pipelines. And the pipelines are what implement the actual rendering and the actual visualization. Colza uses Mochi's scalable service group for group membership, and it relies on Mona, an implementation of MPI-like collective algorithms that is built directly on top of the Mercury RPC library that is used by Mochi. From the simulation's point of view, Colza's API is extremely simple. The simulation first calls an activate function, which tells Colza servers that they should expect some data soon. Then the simulation calls stage to send some data along with the associated metadata. Then it calls execute, which triggers the execution of some pipelines on the servers. And finally, deactivate, which tells the Colza servers that nothing more is expected for this iteration. The activate and deactivate functions are here to enable consistency management, which I will describe next. Group membership in Colza is managed by SSG, which is decentralized and relies on the SWIM gossip protocol to propagate membership information. So to add a server to the group of Colza servers, that server will send a message to some of the existing servers of the group, and the message is going to be relayed to other members via gossip until everybody is aware of the new member. Similarly, if a process or a node wants to leave the group, it's going to first send a message, and the information of this member leaving is going to be propagated via gossip. The activate and deactivate functions that are called by the client, by the simulation, are there to prevent changes to the group in the middle of an iteration, which could lead to undefined behaviors in visualization pipelines that expect the number of processes not to change. So effectively, when we call activate, we ensure that the staging area is not going to change scale until the next deactivate call. Now, one problem with SSG is that the membership information is only eventually consistent. So for instance, one server could have received the information about a new member, while another server does not. And this poses a problem when we start an iteration of analysis, because instances of a pipeline across servers will be expecting that they have a consistent view of the staging area. And to solve this, what we use is a two-phase commit protocol with the simulation itself acting as a controller. The simulation will actually send a try activate RPC to all the known servers, and the servers will respond with a hash of their group view and switch to an activated state. If the hashes received by the simulation don't match up across servers, or if a server does not respond, then the simulation sends a cancellation message and retries. Before it retries, it's going to contact the server and ask that server for its most up-to-date view of the group. Otherwise, if all the hashes are consistent, then the simulation knows that the activation was successful and all the servers are in an activated state and they won't rescale until the next deactivate call. And so the simulation can continue with stage and execute calls. When pipelines execute, they will need to perform collective communications, and for this we implemented Mona, which is directly based on the RPC library used by Mochi. Mona uses unexpected messages for small messages. It then switches to rendezvous for slightly larger messages, and finally it switches to remote direct memory accesses for even larger messages, and the threshold between those different strategies is configurable. The collective operations that it provides are similar to that of MPI, meaning we have broadcast, all gather, reduce, and so on. And currently we implemented them either using naive algorithms or using algorithms inspired by MPitched. We did not try to optimize in particular these algorithms. Our point in this work was really to show that we can replace MPI with something else in existing frameworks. The big advantage of Mona over MPI is that there is no concept of a world communicator. So even though when doing a collective communication, Mona is expecting the communicator not to change, it's very much possible to change a communicator in between those operations. And communicators can be built from any list of Mercury addresses, and it's easy to rebuild communicators when processes join and leave. So as we couple Mona with SSG, we can rebuild a communicator whenever we have a notification that a process joined. Finally, the pipeline part of Colza is where visualization actually happens. Pipelines can be provided by the users in the form of dynamic libraries containing a child class of an abstract pipeline class with the corresponding activate, stage, execute, and deactivate functions. As an example of pipeline that uses an existing in situ visualization framework, we implemented a ParaView pipeline that can take a Python script for Catalyst and execute it on the data that is received by Colza. So this means that we can bring the full power of ParaView, which is a widely used in situ visualization framework and parallel visualization framework in general, and make it elastic thanks to Colza. To do so, we provided our own implementation of the right VTK class using Mona, as well as implementation of the IST communicator structure for the underlying image compositing library IST. We evaluated Colza on the Cori supercomputer from NERSC, and we aim to answer the following questions. First, what is the overhead of Mona compared with MPI? As I said, we did not particularly optimize Mona at this stage, but it's still interesting to see how it compares with MPI. Second, what is the benefit of adding nodes on the fly? What is the overhead of group management? And what is the benefit of rescaling on the visualization time on the server? We first compared Mona against MPI in terms of their point-to-point communication performance. Here you can see the performance for 1,000 send-receive operations using Cray MPitch, OpenMPI, Mona, and we added NA, the low-level messaging library of Mercury, which we use in Mona for comparison. We did not expect Mona to outperform CreMPitch for the simple reason that CreMPitch is a vendor-provided implementation of MPI on Cori. So we do hope that this vendor-provided implementation is as best as it can be. However, we were surprised to see that Mona outperforms OpenMPI for messages that are larger than 2 kilobytes. And we suspect that what's happening is that Mona uses RDMA for larger messages, which might be more efficient than the rendezvous protocol used by OpenMPI. You might be wondering why Mona is outperforming NA, which is a low-level library that it actually uses. And this is because Mona does some clever things with caching and reusing messages and resources across calls that allows to reduce the number of allocations and this kind of things and the number of copies. We then looked at the performance of some collective communication algorithms, and here I'm showing an example with the reduce operation, which is used in particular for image compositing. Here again, we are not surprised to see that Mona does not outperform the vendor-provided MPI implementation, CreMPitch. However, we were really surprised by the poor performance of OpenMPI and to see that Mona actually massively outperforms OpenMPI when using large messages. Next, we use actual applications with data to render to evaluate Colza as a whole. We used a Mandelbrot application, which computes a 3D Mandelbrot fractal. We used then a Gray-Scott reaction diffusion simulation, and we used a deep water impact simulation that I talked about in the first slides. For the deep water impact simulation, we actually relied on data provided by John Patchett from Lanol in place of the actual simulation. And we wrote a proxy application that simply reloads this data and feeds it into Colza. Mandelbrot and Gray-Scott use uniform grids, which are split uniformly across client processes and then distributed across Colza servers. And a deep water impact simulation uses unstructured mesh that is split across a set of VTK files. In the rest of this presentation, we will always use CreMPitch as the implementation of MPI to compare against, since it's the best performing one on that platform. These figures show the execution time of the rendering pipeline with Mona in red and MPI in blue. When we vary the number of Colza servers, we use a weak scaling setup for Mandelbrot, doubling the number of client processes when we double the number of Colza servers. And we use a strong scaling setup for the Gray-Scott simulation, where the same amount of data is rendered with different number of Colza servers. What we can see here is that although there is a difference in performance between MPI and Mona, as we saw in previous slides, when considering a full pipeline, which is more computation intensive, then it does not really matter anymore that we use a slightly slower communication layer and the rendering time is about the same. Now, in Mandelbrot and Gray-Scott, the amount of data doesn't change from one iteration to the next. But with deep water impact, it does. So here you can see the rendering time as the simulation actually progresses and actually produces more and more data and data that is more and more complex, with different number of Colza servers represented in different colors and with MPI represented in dash for comparison. In practice, what we can see here is that Mona either has a slight, I would say negligible overhead over MPI, or in many iterations, it actually outperforms MPI. We also compared Colza with two other frameworks for in situ visualizations, namely Damaris and Dataspaces, using the Mandelbrot application. We were able to do so by porting our visualization pipeline as a Damaris plugin and as a Dataspaces plugin. Both of these frameworks use MPI internally for visualization. Colza with MPI outperforms all of them. Then comes Dataspaces, then Colza with Mona, and finally Damaris is the slowest. However, contrary to these frameworks, Colza is elastic. Besides, Damaris imposes much more constraints on the simulation. Its coupling to the simulation is done via MPI, and the number of servers must divide the number of clients, which imposes a restriction on the scale at which the visualization can run. Data spaces is an interesting use case because it also uses Mochi for communications with the simulation. But again, it's not elastic, contrary to Colza. However, we can expect that since it uses Mochi, all the work that we've done here could be ported to it. Let's move on to some actual elasticity experiments where we actually run the simulation, Colza, and change the number of processes without shutting everything down. Here we took the Mandelbulb application and started with 2 Colza servers, and we added 1 new server every 60 seconds. Every time a server is added, you can see that the visualization time slightly increases for 1 iteration. And this is because the new server has to initialize VTK, which means dynamically loading many libraries from the parallel file system. But then overall, the rendering time decreases. Since we do not expect rescaling to be a frequent operation, this kind of overhead is acceptable, and we can see here that by increasing the number of Colza servers, we can improve the rendering performance, and we can do so without shutting down the simulation. We also evaluated elasticity with the deep water impact simulation, and here what we did is we started with 1 Colza server with 8 processes, and after iteration 13 of the simulation, we started adding 8 processes every other iteration. And we can see here again that each time a new set of processes is added in Colza, there is an overhead due to the initialization of VTK, but then the rendering time goes back down, and overall the use of elasticity allows the rendering time to remain bounded under 20 seconds per iteration. Even 10 seconds if we don't account for the overhead of initializing VTK. By comparison, not using elasticity means that the runtime goes much higher in proportion with the amount of data that has to be rendered, up to nearly 40 seconds toward the end. Now the question is, what could we do with such elasticity? Well, elasticity could be user-driven, meaning that a user may want to add or remove resources at runtime depending on what they want to do with the data at a given moment. We can imagine that something interesting happens, the user notices it in some light diagnostics, light data visualization, and starts to want to add more complex rendering. It could be performance driven. For instance, we could imagine having a monitoring service that monitors the performance of the simulation and the performance of the rendering and tries to achieve a full overlap between the simulation and the visualization by adding and removing processes accordingly. It could be data driven. We could have some modules that detects whether some interesting phenomenon appears in the data, and if so, add more resources to perform some more complex visualization scenarios. And we could also imagine that the job scheduler could talk with the job itself in order to reclaim resources if those resources are needed, for instance, by another job, and add more resources later. So if the job scheduler could know ahead of time that a certain job can accommodate some flexibility in its resources, then it could interact with that job and add and remove resources. As a conclusion, elasticity could have clear benefits for applications, especially if they have irregular data products. We have shown here that elasticity is possible using existing frameworks by replacing MPI, and that replacing MPI can be done without a significant performance overhead. That said, I hope that this work will encourage the MPI forum to provide some elasticity features in the future. Moving forward, we want to see if this kind of elasticity can be used for fault tolerance, in particular because fault tolerance is the primary use case for the SWIM protocol. We also want to enable stateful pipelines, which will require some data redistribution when rescaling, and that's something that we can do with another Mochi component called buffer scale. Also, we want to see how this kind of work can be integrated with job schedulers in practice. Thank you for your attention.